Good morning, everyone. In the previous session, we have discussed in detail about different criteria for choice of recovery process, and we have also discussed in detail about the principles of precipitation and flotation in the recovery and purification process. In today's class, we will discuss on various other methods such as filtration, centrifugation, and we will also discuss about the recovery of the solvent. So in continuation of the previous session, we have seen what are the typical agents used in precipitation process which makes or render the compound of interest insoluble. Number one is the acids and bases. So to change the pH of a solution until it reaches the isoelectric point of the analyte or compound or the product of interest, and when pH equals Pi, there will be no overall charge on the molecule. So its solubility is decreased. So this is one of the important component to make or render the compound or the analyte or the product of our interest insoluble. And second, we have salts such as ammonium sulfate and sodium sulfate. So these salts are used for the recovery and fractionation of proteins. You people are very well aware of the term salting out. So what is all about this? The salt removes water from the surface of the protein so that the hydrophobic moieties are revealed. Then they come together causing the protein to precipitate out of the solution. So the most hydrophobic proteins, that means the hydrophobicity of the protein, if it is more, that protein precipitate first. Right, this technique is called as salting out of proteins by using ammonium and sodium salts. So the salt removes water from the surface of the protein, revealing the hydrophobic patches. Then they come together causing or making the protein to precipitate out of the solution. So more the hydrophobicity, the protein precipitate first. So we call it as salting out of the proteins. So this is another approach. Then we have organic solvents. So the dextrans can be precipitated out of the broth by addition of methanol. Even the chilled ethanol and acetone can be used in the precipitation of proteins for the reason that they change the dielectric properties of the solution. Right? So dextrans, they can be easily precipitated out from the fermentation broth by the addition of methanol, and even chilled ethanol and acetone can be used to precipitate the proteins, and it happens mainly due to changes in the dielectric properties of the solution. Then we have polyethylene glycol, the non-ionic polymers. These can be used in the precipitation of proteins, and their behavior is very much similar to the organic solvents discussed above. Then we have polyelectrolytes. These can also be used in the precipitation of a range of compounds. Right? And next we have protein binding dyes. As an example, I have given triazine dyes. They bind to and precipitate certain groups or certain classes of protein. Then we have affinity precipitants. So these affinity precipitants, they are an area of much interest in the present days, and they are capable enough to bind to and precipitate compounds selectively. That is most important, selective precipitation, so that you obtain the product of interest in desired quantity. And finally, we have heat treatment as a selective precipitation and purification step for various thermostable products. If the product is thermostable, then this precipitation method, that is heat treatment as a selective precipitation and purification step, is very useful. Right? And next, moving on further, we have filtration. Filtration is one of the most common process which is used at all scales or levels of operation, that is unit operations, to separate suspended particles from a liquid or gas using a porous medium. Now this medium retains the particles, but it allows the liquid or gas to pass through. So it is one of the most common process used at different levels or scales of unit operations in the fermentation process, for the reason to separate suspended particles from a liquid or gas using a porous medium, which finally retains the particles and allows only the liquid or gas to pass through. So it is possible to carry out filtration under a variety of conditions, but the number of factors, there are several factors which influence the choice of the most suitable type of filtration aid or the filtration equipment. It is possible, no doubt, to carry out filtration under a variety of conditions. It allows to do so, but there are a number of factors which obviously influence the choice of the most suitable type of the equipment to meet the specified requirements at minimal overall cost. Now, what are those obviously influencing factors? Number one, the properties of the filtrate, particularly with respect to its viscosity and density. Number two, the nature of the solid particles, particularly their size and shape. The size distribution and packing characteristics also play a significant role. Number three, the solid liquid ratio. Number four, the need for recovery of the solid or liquid fraction, or maybe even both. Number five, the scale of operation. Number six, the need for batch or continuous operation. Number seven, the need for aseptic conditions. Number eight, the need for pressure or vacuum suction to ensure an adequate flow rate of the liquid. So these are some of the important influencing factors on choice of the filtration technique or the equipment or the aid. Moving on to the next unit operation is the centrifugation. So the microorganisms and other smaller size particles, they can be easily removed by the use of centrifuge. That is, from the fermentation broth, the microorganisms and other similar small sized particles, they can be easily taken out or removed from the fermentation broth using a centrifuge. When do we go for centrifugation? When the filtration is not a satisfactory separation method, because centrifugation is an expensive approach when compared to the filtration, but it becomes essential when filtration is slow and difficult. When the cells or other suspended matter, they must be obtained free of filter aids, and continuous separation to a high standard of hygiene is required. When there is a continuous separation to a high standard of hygiene is required. Right? So the microorganisms or any other smaller sized particles, they can be easily removed by the process of centrifugation. But when we go for centrifugation, that means we are not satisfied with the filtration step. When the filtration is not a satisfactory separation method, then centrifugation becomes essential. When it becomes essential, when the filtration is not satisfying, that means when the filtration is slow and difficult, when the cells or other suspended matter, when it has to be obtained free of filter aids, and when continuous separation to a high standard of hygiene is required. Then we have cell disruption. And we know that microorganisms are protected to the best by extremely tough cell walls. So in order to release their cell contents, cell disintegration method or the improvements in various cell disintegration methods is very much important. So whatever the potential method or the method of disruption or the cell disintegration method you adopt, you must ensure that labile materials are not denatured by the process or hydrolyzed by enzymes present within the cell. So just breaking the cell wall is not the only agenda. You must ensure that the labile materials within the cell are not denatured by the process or hydrolyzed by enzymes present within the cells. Right. So some of the methods are the and which comes under physico-mechanical methods. Number 1, liquid shear, solid shear, agitation using abrasives, freezing and thawing, then ultrasonification using ultrasounds, then hydrodynamic cavitation. So these are some of the physico-mechanical methods that can be adopted for cell disintegration or disruption, ensuring that the labile products are not degraded. Liquid shear, solid shear, agitation with abrasives, freezing and thawing, ultrasonication, and hydrodynamic cavitation. So these are some of the physico-mechanical methods. Then we have chemical and biological methods. Use of detergents, osmotic shock, alkali treatment, enzyme treatment, and finally use of solvents. All these are for cell disintegration or cell disruption. That is use of detergents, osmotic shock, alkali treatment, enzyme treatment, and solvents, use of solvents. Right. So moving to the next method, that is liquid extraction. So we have been trying to understand various recovery and purification methods. Now we are at a point to understand the liquid extraction. The separation of a component from a liquid mixture by treatment with a solvent in which the desired component is preferentially soluble. Alright, that means separation of a component from a liquid mixture by treatment with a solvent in which the desired component is preferentially soluble is known as liquid-liquid extraction. That means you are extracting your product from the liquid mixture by use of another liquid or another solvent wherein the product is soluble, preferentially soluble in the another solvent. It is already present in one liquid and you expect that it gets dissolved in another solvent. So this process is called as liquid-liquid extraction. Right. So prior to starting a large scale extraction, it is important to find out on a small scale or a pilot scale the solubility characteristics of the product using a wide range of solvents. So you cannot straight away take it to the large scale extraction method. The product is already in one liquid. How to get the product out of that liquid? So you employ another solvent, another liquid, so that the product, only the product is soluble in that liquid, in the second liquid, and you call this process as liquid-liquid extraction. So to carry out this, you cannot straight away go for large scale extraction. It is important to find out on a small scale the solubility characteristics of the product, whether the product of or what we are speaking is soluble in solvent A, B, C, D, N number. So you have to confirm at small scale the solubility characteristics of the product using wide range of solvents. So there is a simple rule to remember is that like dissolves like. So most of the chemistry students will be aware of this rule. The rule is like dissolves like. So the important likeness as far as solubility reactions are concerned is in the polarity of the molecules. Polar liquids mix with each other and dissolve salts and other polar solids. The solvents for non-polar compounds are liquids of low or nil or zero polarity. Is that clear? Right. Now this table gives you an idea about various solvent system and their dielectric constant. So it is from the least polar to the most polar, from hexane up to water. Now this dielectric constant is a measure of the degree of molar polarization of the compound. If this value is known, it is then possible to predict whether a compound will be polar or non-polar, with a high value indicating a highly polar nature of the compound. Right. So the dielectric constant is a measure of the degree of molar polarization of a compound. So if you can know this value, then it is possible to predict whether a compound will be polar or non-polar, with a high value indicating a highly polar compound. So the final choice of solvent will be influenced by the distribution of something called as partition coefficient, denoted by K. Right? So where the value of K, it defines the ease of extraction. How do you determine the value of the K? It is the concentration of solute in extract over concentration of solute in raffinate. So the final choice of solvent is, or it will be influenced by the distribution or partition coefficient denoted by the letter K, and this value of K, it defines the ease of the process of extraction. Now what is K? K is the concentration of solute in extract over concentration of the solute in the raffinate. When there is a relatively high value of K or relatively high K value, good stability of product and good separation of the aqueous and solvent phases, and then it may be possible to use a single stage extraction system. So you have single stage extraction system and multi-stage extraction system. So when there is a relatively high K value, right, that means the concentration of solute in extract over concentration of solute in raffinate. When there is high K value, good stability of the product and good separation of the aqueous and solvent phases, it can be expected, and then it may be possible to use a single stage extraction system. This is an diagram which shows the single stage extraction unit. That means we have one drain, we have the solvent feed, aqueous feed, and aqueous feed. So it is a single stage extraction unit, right? But unfortunately, in a number of systems, the value of K, that is partition coefficient value, is low. So a co-current or counter-current multi-stage system needs to be utilized. So this figure in 10.26, it is a simple diagram of a co-current flow extraction system. It is beautifully illustrated how the co-current flow extraction works. If you just carefully look at the figure, there are n number of mixer or separator vessels. That is 1, 2, and it continues n number. They are all in one line, and the raffinate goes from vessel 1 to vessel 2 and it goes up to vessel number n. The fresh solvent is added at each stage. The feed and extracting solvent passes through the cascade in the same direction. Now extract is recovered from each stage. So it is, although a relatively large amount of solvent is used, a high degree of extraction is achievable. Got it? Carefully understand, this is a multi-stage system. We call it as co-current multi-stage system. There are n number of mixer or separator vessels, and all these n number of mixer or separator vessels are arranged in a line, and the raffinate goes from vessel 1 up to vessel n number, and the fresh solvent is added at each stage. The feed and extracting solvent passes through the cascade in the same direction. You can see the arrow marks. It is passing through the same direction, and extract is recovered from each stage. So you can recover the extract from separator 1, separator 2, and you can go up to separator n. Although it is a relatively large amount of solvent is being used, a higher degree of extraction is achievable in co-current flow extraction system. Right. Then we have another extraction system, that is counter current extraction system. So this diagram 10.27 gives you an idea about the working method of the counter current extraction system. There are a number of mixer or separators. They are connected in series. Again, we have mixer or separator number 1, number 2, and it goes up to n number. Right. The extracted raffinate passes from vessel 1 up to vessel n. Right. Now what is the difference? Now difference comes here. While the product enriched solvent is flowing from vessel n to vessel 1. The extracted raffinate passes from vessel 1 to the nth number of the vessel, whereas the product enriched solvent is flowing from nth vessel up to vessel number 1. The feed and extracting solvent passes through the cascade in opposite direction. That is why the name counter current extraction system. In co-current, it is in the same direction, whereas in counter current, the feed and extracting solvent passes through the cascade in opposite direction. The most efficient system for solvent utilization is the counter current operation. So it shows a considerable advantage over the co-current system, because in co-current system there is use of relatively large amount of solvent, but in counter current system you need not use a large amount of solvent. So it is an advantage, a considerable advantage over co-current extraction system. Is that clear? So we have counter current and co-current extraction system. So in co-current extraction system, the feed and extracting solvent passes through a cascade in the same direction, that is from vessel 1 to nth number of the vessel. Whereas in counter current extraction system, the feed and extracting solvent passes through the cascade in opposite direction, that is from nth number of vessel up to vessel number 1. Right. So next we have recovery of the solvent. The major item of equipment in an extraction process is the solvent recovery plant or the unit. Usually it will be a distillation unit. Right. It is not normally essential to remove all the raffinate from the solvent, because most of the time it will be recycled. And in some process, the more difficult problem will be to remove all the solvent from the raffinate, because number one, the value of the solvent may be very much expensive, and number two, contamination of the product. That's the reason it becomes very difficult to address the issue of the cost of the solvent and contamination of the product. So some process will require to remove all the solvents from the raffinate, because the solvent might be too expensive, so you cannot afford to lose the solvent, because essentially you are using the solvent in a larger quantity. And second thing, the solvent might be a contaminating issue in the recovery and purification of the product. And we know that distillation is the step in the solvent recovery. And distillation may be achieved in three stages. Number one, evaporation. That is removal of solvent as a vapor from a solution, which is an most sought and most common or often used method. Number two, vapor liquid separation in a column. So that to separate the lower boiling point more volatile component from other less volatile components. And then we have condensation of the vapor to recover the more volatile solvent fraction. So you can have three different stages where the distillation is achieved. Number one, evaporation, vapor liquid separation, and condensation of the vapor. Right? So I'll stop my discussion for today here. We'll continue our discussion on some more aspects of the purification process, and then we will see how the different products which are mentioned in your curriculum, how they are recovered or purified by understanding in much details. So thank you very much for your kind listening.